This is David Spears, Civil Engineering Instructor at Texas Tech University, talking about Sttics CE 2301. This is a simple mass moment of inertia problem. It was from a sample quiz. What it consists of is an assembly that looks like a dumbbell, but it's really a sphere on the left side and a cylinder on the right side, and connected by a rod. The masses are given here: 24 kilograms, 6 and 15 kilograms for the pieces, and we're given the dimensions. The radius of the sphere and the cylinder is 500 millimeters, or half a meter. The length of the rod is 1 meter. So this is a sphere or a ball at this end and a cylinder coming out of the plane of the board at this end. Okay, well, also we gave you a chart with the mass moments of inertia about each piece's centroid. And remember, when we're talking about mass moment of inertia, we're talking about the resistance to rotation about an axis. In the case of all three of these things, the axis comes out of the page. So the centroidal mass moment of inertia of each piece is given by this formula over here. For the sphere, it's 2/5 the mass times the radius squared. For the rod, it's 1/12 the mass times the length of it squared. And for the cylinder, it's 1/2 mass times radius squared. So that's for rotating individually each piece about the centroid. That center of that sphere, the center of the rod, and the center of the cylinder. So, I like to break these up into these little charts. Look a lot like these central moment of inertia charts that we were making, except instead of areas, we're dealing with masses. Okay, the first problem is, what is the centroid in this direction, X, as I've chosen to call it, from this point O that I've drawn here in red, the distance to the mass center of the entire assembly. And so I have a row for the sphere, the rod, and the cylinder, and those are the masses that I've already written in. Let's find the centroids. The centroid of the sphere is the radius, 0.5 of a meter away from point O. So I just write 0.5 in there. The center of that rod is the diameter of the sphere, which is 1 meter, plus half the length of the rod, half a meter, so it's 1.5 meters. And for the center of the cylinder is at 1 plus 1 plus a half, 2.5 meters. Now, just like I was doing for area to get the centroid, I just multiply the mass times what I've called the x tilde distance from my reference point to the centroids. And the math here is at 24 times 0.5 is 12, 6 times 1.5 is 9, and 15 times 2.5 is 37.5. Now I add all those up, and I get 58.5. And I've already added up the masses, get 45 kilograms. So X bar is just equal to the sum of the x tilde m's divided by the sum of the mass. So that's just 58.5 divided by 45. And it makes it equal to 1.30 meters. Okay, just like the areas, except we're dealing with masses. Okay, the second part was the mass moment of inertia about point O. So that is using the parallel axis theorem, which is that IO is equal to the sum of the individual pieces, moments of inertia about their centroid, plus md, in this case x squared. So first I need to get the individual centroid, the moment of inertia, mass moment of inertia about the centroid. And once again, I'm dealing with the z-axis. That's what I want to know about point O too. What's the resistance to rotation about that about an axis coming out of the board at point O? This whole thing revolving around it. So I do the math on these. Here I've plugged in the numbers, and I just, for the sphere, it's this product, which is 2.4. The units are kilogram meters squared for all these. Kilogram meters squared. The math here works out to be 0.5, 6/12. And for this one, for the cylinder, it's 1.875. Note I've just taken these formulas and just put them down here and put the numbers to them and then done the math. Okay, the individual pieces is not, the contribution to the overall mass moment of inertia about point O is not very great, but these mx squared terms get to be pretty big. With the parallel axis theorem, I just want to know the distance from the centroid of the piece to the point, to the axis, to a point on the axis that I'm taking a mass moment of inertia about. So that just conveniently is this x tilde distance. So I just do the math. 24 times 0.5 squared is 6. Same units, mass times distance squared, mass times meters squared. 6 times 1.5 squared is 13.5. 15 kilograms times 2.5 squared is a big number compared to everything else, 93.75. Add all those up, I get 113.25. And I need to add all these up, and that's 4.775. And my answer here is the sum of those two numbers, and so that equals 118.0 kilogram meters squared. Okay, lastly I need to do the radius of gyration with respect to point O, and that's what we call KO, which is equal to the square root of the mass moment of inertia about O divided by the mass. So it's an easy calculation. I've got both of my numbers. It's the square root of 118 divided by 45, which is equal to 1.619 or 1.62 meters.